Let's start. Recently, uh, I'm reading a paper which where which studies the non-perturbative effect in the jet gravity. Actually, it just give an alternative method to calculate the exact density distribution for the random matrix theory. I think actually is just something like the decomposition problem. Uh, the key point of this paper is just to do the double scanning and to define for the discrete case. That is, you imagine that we are dealing with a matrix, n-dimensional matrix, so it has an eigenvalue. Then it is a random matrix, so that we can define the uh, orthogonal polynomials. Then, if you can find the orthogonal polynomials, then and then in principle you can solve any question about the random matrix system. Oh, okay. This is the key point of this paper. And okay, let's begin. And the author has written a series of paper about these topics, and this one has how to say has more details. So I choose it as an example. Anyway, something I just forget it. One target or one motivation of this paper is just to understand the spectral density of the jet gravity. We know that the jet gravity, we just calculated its partition function z beta, and we found that it corresponding to sum over all Riemann surface with an asymptotic boundary which has the length beta. Okay, you just sum over it. Then we consider that for each genus we attach it with a factor e to s0. No, e to minus s0. So high genus contribution is suppressed, so we just consider the needing order. The needing order is just the disk topology. Then you calculate the beta at the disk topology, then you can do the inverse transformation to get the needing spec density. Then you find that it is continuous. Yes, it's continuous. So how to understand this case? So for myself, I think that to myself it's just a large n approximation, a large n limit for the random matrix theory. So when in that case, you can, because it's random, it's density, the eigenvalue should omit to a continuous distribution. So it is I think it is quite nature. It's nothing non-trivial. Okay. Sorry. There's nothing non-trivial. Then let's try to understand the paper. Anyway, but the paper want to give another explanation for this case. It just want to argue that we can think that the distribution of the density the density of the eigen values correspond to some quantum system. This quantum systems has discrete eigenvalue, but we need to do average of the quantum ensembles. Sorry, ensembles. So so actually we get many smooth curves. We sum over all the curves, then we got the total density distribution. Maybe we can the picture. This is a picture. The black line represents the non-perturbative density, and the first one, the first curve here, it represents the distribution of the ground state energy, and this one is for the second state, this is for third state. Due to that, the what we consider is an ensemble of quantum system. So you will not see a discrete spectrum. You just see some continuous curve, and he just defines the average of every of any of each curve as some energy as En. Then this picture just the first picture just plotted. Okay, this one. Okay, this one. This is the average of E for the first curve for the ground state distribution. I think from the point of view of mathematics, it's just a decomposition. It's nothing. I think nothing from this. Anyway, to my interest, I want to know what is the non-perturbative contributions. I don't see it. But anyway, it has some things. It's quite interesting. Yes, we just write the density of the eigenvalue of the random matrix as how to say, as a contribution of all of a random quantum system. This is the nth eigenvalue of the quantum system. Okay, that's great. Actually, what we need to do, in principle, it is just a decomposition program. First I need to, maybe I need to use this one. This one. Okay, I'll try. Okay, that's great. Let me see. Yes, we from just from the point of view of math, we just want to study the partition function like this. It's z. Okay, z. You can insert some anything like a trace hk and any other things. Then this is the partition function. Then we he just regard this thing. The xp is exponent as a weight, and he want to know. We want to construct the orthogonal polynomials for this weight. Then you can write any polynomials of lambda as the orthogonal polynomials. Then it's quite easy and direct to calculate the partition function and any correlation function. Sorry. Yes, that's great. Then what we need to do is to take the limit, take the large n limit. Okay, that's great. And notice that we need to do another limit, that is a double scaled limit, because we want to compare the results of the random matrix theory to the jet gravity theory. So we need to do the double scale limit. In a word, the double scale limit is just to zoom in. You just to take care of the distribution at the edge. Okay. At the edge. Okay. Just take care of this one. This thing. So you need to zoom in. Okay. Anyway, this is what we want to consider. Okay. It's quite easy. It's quite easy and direct to calculate the needing density distribution. Yes, it's quite easy. Okay. Then, but this paper we want to study the non-perturbative effect. Actually, for large n, the non-perturbative effect is quite small, I think. Yes, but you want to perform it. So in this paper, we just use uh H bar, like H bar in quantum mechanics to denote the non-perturbative effect. It should be 1/n, I think. Maybe not here. Anyway, we will talk it. Okay, here it's it. Anyway, at first we need to find the orthogonal polynomials. It's quite easy to calculate. I mean, because I think that many mathematicians have sort of it, so you can just use the conclusion. Okay. Anyway, then our task is calculate Hn. No, you don't need to. Actually, you don't need to use it for the Gaussian model. You know that the polynomial is just the Hermite polynomials. That's great, quite easy. And you will find that the determinant of the matrix can be written as a product. Oh no, anyway, as some product of the orthogonal polynomials. So finally, you can find that the partition function is quite easy to calculate. And the recursion relation can help us to calculate. Okay, the recursion relation is useful. Okay, then our target is calculating Rn. Why? That's because how to say, the partition function can be written in a form in terms of Rn, not Hn. Okay. For the Hermite polynomials, it's quite easy to calculate Rn equal to n minus the largest. Then you will take that the n equal to infinity. So Rn should be a smooth function of x. X ranging from 0 to 1. Okay, that's great. And here we choose the v lambda to be even. So you can find that this one equal to 0 because this part is just an odd function. This one is an even function, and the integral range from minus infinity to positive infinity. So this gives 0. And then it's quite, and then you can calculate this one. Oh, it's quite straightforward to calculate it. Anyway, you can check it with the recursion relation. Okay, now finally you get this one. Okay, great. Then for any for an explicit form of v lambda prime, you can use the recursion relation to write it as a comparison of the polynomials. So then use the definition of the orthogonal polynomials. You can calculate that the left-hand side must be something times h n minus 1. So you can cancel h n minus 1 on both sides. So you will got an equation for Rn. For example, for the next non-trivial case, you can find that the result is quite easy. What? Okay. That is quite easy. Okay. This is for the discrete case, then we just need to do the continuous limit. Okay. Okay, that's great. You see that the tilde is fixed by Rn. Okay. So then it's quite easy to calculate Rn. For a leading case, you just take n to infinity, Rn to go to Rx, and then you can solve it. But what we want to do is just to zoom in to the double scale limit. So we just take care of the distribution that's very near to the edge. So we take that the x equal to 1, sorry, 1 plus some infinitesimal things. The delta 2k, we take delta, the parameter delta go to 0 in the limit. Anyway, and the key is some positive integrity to be fixed to determine the order of the potential. Yes, for different potential, we have different or different behavior of the distribution at the edge. So, and we define h bar over this equation. Then we just write the coefficient, this one for x. You put x expression in it. Okay. Then our target is to give equation to determine u. Okay. If I actually just to use this equation or this equation anyway. For example, for the next non-trivial case, we have known that this one, okay. Then you see that this part and this part will give the second derivative of r, okay. Then just to write it down. Then you put everything in it. Here there is some subtlety that we need to shift the critical value G4. At the beginning, it is just a constant. It is just constant, but now we just shift it with delta. It's okay because finally we will take delta equal to 0. Okay, and we will require this equation to be held for order by order for the delta. Okay. Then we take k equal to. We require that the delta, the order, there's a 0 order and the second order can cancel to 0. So we can fix something. Yes, we can fix G4. Yes, we can fix G4. Oh, it's interesting. Why we can fix G4? We know that we can fix G4S, but I think that G4C is fixed, I think. So maybe I have made some mistake. Yes, I made some problem when I try to recover this result. Yes, I use mathematics. Okay. But I found that we need to do the shift that mu go to x, then we can go to, okay, this time go to 0. It gives the right equation. But I don't know why we need to do this shift. And just now I think that we cannot take GC to a constant. Oh.
地感层面镜。
哎，
我问你一下，那个，PRD 的叫样是怎么叫啊？
不用怎么叫吧？
你直接